In this video, our question is, what are the components of an electric circuit? And to understand what an electric circuit is and its components, we must first understand what causes electricity. Electricity is caused by the movement of electrons. The electrons within an object, like a light bulb, begin moving. And once those objects within the light bulb, once those electrons within the light bulb begin moving, that is what causes, in this case, the filament of the light bulb to glow. It gets red hot from all that movement and friction of the electrons, and that then gives off the light energy, which we associate with the light bulb. Now, the question is, what makes those electrons move? What starts them moving in the first place? Typically, electrons aren't moving within the filament of the light bulb in any kind of organized fashion. So what makes the electrons move is a battery or voltage. So the light bulb itself doesn't glow unless you connect it to a battery, in which case we get those electrons to start to move. Now there are three different components to any kind of electric circuit. We must have the voltage, and the voltage is what makes the electrons move. This would be the battery in our circuit. The symbol for the voltage is V, V for voltage, and the units are volts, which kind of looks like the word voltage itself. So we have the voltage here. The second component is the current. And think about in terms of a current, like a current in a river. Current in a river is how fast the water is traveling. Well, current in electricity is how fast the electrons are moving, how fast the electrons are traveling. The symbol is the letter I. This is the one that really doesn't make sense. It is not C for current, but I. And nobody knows for sure why they chose the letter I, but they speculate that the letter I comes from the word intensity. They're talking in the very beginning when they're talking about electricity, they're talking about how intense the circuit was, how intense the electricity was, how intense the charge was. And so the letter I, they think, comes from that word intensity. The units are the ampere, or amps for short. A lot of times we use the letter A to abbreviate for amperes. The last part of the circuit is the resistance. And this is what prevents or resists the electrons from moving. And it might seem kind of odd, why would we have something that makes the electrons move and also have something that resists or prevents the electrons from moving? Well, getting the electrons to move themselves is of no help. It's of no use. Moving electrons don't help us at all. Instead, we have to use the energy of the moving electrons and transfer it into something that's more beneficial. So in the situation of our light bulb, the fact that the electrons are moving is no big help. What the light bulb does is the light bulb slows the electrons down and steals their energy. And after it steals their energy, it is able to convert that energy into a different form. In this case, it converts it into light. So essentially, this resistance is meant to take the energy from the electron and to convert it into a more useful form. So it might convert it into light, or we might have something like a radio, which converts the electricity into sound. Or we might have something like a fan, which converts it into motion to cool us off. So we have lots of different ways of changing this energy into different forms. Forms that are a bit more helpful or a bit more useful to us. Now the symbol for resistance is the letter R, R for resistance, and it's measured in a unit called ohms. Now we use the letter V for volts, the letter A for amps, but we don't want to use the letter O for ohms, because if I have something that is 8 ohms, and I write 8 O, it looks like I have 8. So instead what we do is we use the Greek letter O, which is omega, and that is this symbol then for ohms. Now the way that all three of these values are connected to each other is through something called Ohm's law. And Ohm's law is written as the voltage is equal to the current times the resistance. And I have it here in our familiar form that we've been using in class as more of a circle, where V is the voltage, I is the current, R is the resistance. V is measured in volts, I is measured in amperes, and R is measured in ohms. Now we're going to look at each of these components in a bit more detail now. We're going to start with voltage, and voltage, we can get the voltage from really two different sources. The first source we might get voltage from is a battery. And typically batteries come in sizes of AAA, AA, then you have C cell and D cell. And all of those batteries have the same voltage. They all are 1.5 volts. Now there are some other batteries that come in different sizes. Of course, there's the 9-volt battery. The 9-volt battery is the one that looks like a box and it has 2 bumps at the top. And that would be a 9 volts. But most of your batteries are going to come in 1.5 volts. And then what we do is we combine them together to make different voltages like 3 volts or 6 volts or things like that. Now, the other place we can get voltage is from an outlet. And typical outlets here in the United States are at 120 volts. But there are 2 outlets that you have that are actually at more of like 220 or 240 volts, and that is your stove and your dryer. Now this voltage is not always the same. It does fluctuate as supply and demand occurs, and as the power plants produce more or less electricity to try and keep it within a range here of about 110 to 120 volts. So again, they try and keep it within a certain range. But there are those 2 outlets, your stove and your dryer, which do operate on a higher voltage, and those are somewhere between like 220 and 240 volts. They require a higher value, a higher amount of voltage. Your typical outlet looks something like this. And your stove and your dryer, it depends. They don't all look the same. It might look something like this here. But they come in all different varieties. There's always those 3 prongs. The one prong is the hot, we say. The other is the neutral. And then the third one is always the ground. Now, in terms of batteries, we have things like positive and negative. We don't have things like hot, neutral, and ground. It's just the way that the electricity is produced. Which brings us to our next thing, the 2 different types of electric current, which is alternating current, or AC, and direct current, which is DC. Alternating current comes from the outlets, which have your hot and your neutral. And what happens in an alternating current is exactly what alternate means to do, to change direction in this case. So the electrons sometimes move one way, and then sometimes move the other way. It's more of like a back and forth, like the tides in the ocean. Goes in and out. It kind of moves back and forth. Direct current means that the electrons are always moving in the same direction. That they are moving towards, in this case, the positive terminal of the battery and away from the negative terminal of the battery. So direct current comes from batteries, whereas alternating current comes from outlets. And so again, the difference is alternating current, the electrons move back and forth, whereas direct current, the electrons are always moving towards that positive terminal. Now, last thing we want to talk a bit more in detail is resistance. And more specifically, we want to talk about the resistance in a wire. Unfortunately, when we send the electricity from the power plant to your house, so we might have a power plant sending electricity through the wires, through the telephone wires, to your house. The wires that we send them along have a lot of resistance. And we want to have as little resistance as possible. So what are some of the things we can do to lessen the resistance and therefore lessen the amount of electricity lost or energy lost in the wires as we send them to your house? Well, one way we could do this is to shorten the length of the wire. So one thing that affects the resistance of a wire is the length. The shorter it is, the less resistance. So we don't want to send this electricity over long distances. We want our power plants to be as close to our businesses and our houses as possible. The other thing is cross-sectional area or width. The wider the wire, the less resistance you have. So we want these wires here to be a lot thicker than maybe the wires within your house or the wires on different electrical circuits in your phones and your calculators and TVs. The other thing is material. Different materials have less resistance than others. Copper has a very low amount of resistance, which is why most of our wires in our houses, our wires are made out of copper because they have less resistance. We don't lose as much energy as the electricity goes through our house. And the last is the temperature. The colder the temperature, the less resistance. That's usually not something that we have much control over, but the cooler it is, the less resistance it has. Now, to create an analogy here of all of this and what we've been talking about, let's kind of compare electric circuits to us walking through the hallways. And so the current in this case would not be the moving of electrons, it would be how fast the students are moving through the hallways. So the current tells us how fast. In this case, how fast the students are moving. The voltage would be like the teachers who make the students move to their next class on time. So remember, voltage is what makes the electrons move. So in this case, what's making the students move is the teachers. And finally, the resistance, what prevents the students from getting to class on time? Well, that in this case would be other students getting in your way or distracting you from getting to your class. And we notice here, if we talk about like with the wires, the hallways would be like wires. And the shorter the hallway, the less resistance you encounter. And the wider the hallway, the less resistance you encounter because you can get around those other students. The last thing we want to talk about here is power. This is really a combination of current and voltage. Power is how fast the electrical energy is being used. It's more of a speed thing. Symbol is letter P, and the unit is measured in watts. We use letter W for watts. Our equation is that the power is the current times the voltage, or drawing it like our circle here when we do our formulas to make the math a little easier. We have P for power, I for current, and V for voltage. Now what a light bulb, let's say, that has 60 watts, what that represents is that the light bulb is using up 60 joules of energy every second. Versus a 100-watt light bulb, which uses 100 joules of energy every second. Now, since the 100-watt light bulb uses more energy every second, it burns brighter. But unfortunately, it will also cost you more because more energy is being used.